In the last lecture, we have learned a lot about the theoretical part of artificial neural networks, and we have used sklearn to program a simple linear regression. What we haven't done yet is to use Keras for simple linear regression. So let us implement the translation from degrees Celsius to degrees Fahrenheit with Keras using a single neuron. We first need to start with the imports again and import numpy, s, and p. And as we want to do some plotting, we import matplot.pyplot as plt. Now we add the Keras packages that we will need and import it from TensorFlow. Furthermore, we will need the following lines from TensorFlow.keras.models import sequential, and from TensorFlow.keras.layers import dense. Next, we need our training data once again, which I will just copy. X is again the measurements in degrees Celsius and Y the measurements of degrees Fahrenheit. Setting up a simple sequential model just takes a couple of lines with Keras. We just need a variable which I will call model again and call sequential behind this variable. This sequential is the one that we just imported up here. You can imagine that the variable model here now holds an empty shell of a sequential model, which we will now fill with a network. And to fill it with a neuron, we call the model and add something to it. In this case, we add a dense layer. Remember that a dense layer is nothing else than a layer holding a specific number of neurons. In this case, one neuron. As this is our first layer in the model, we need to give Keras information about the data shape that we will push through it. This is always written as a tuple, and as we only have one measurement at a time, we write 1, comma into the brackets. And that is already the code to set up our model with only one neuron. Next, we need to specify the optimizer we want to use, and I will save this information in a variable called opt. Here I call keras.optimizers.sgd for stochastic gradient descent and specify a corresponding learning rate of, let's say, 0.002. The next part is already about compiling the model. Therefore, we call our model, say compile, and provide our optimizer, as well as the loss function, for which I will use the mean squared error. Just like with the linear regression, we train the model by calling the model and say .fit, followed by the input data x and y, and the number of epochs we want to use. I will use 1500 for now. Let's recall that one epoch means that the training data is passed through the model one time, meaning the model will look at our data 1500 times in this case. As we want to be able to track the training progress later, we can put this line of code behind a variable which I will call history. So let's run this cell and start the training process, which will take some time now. As you can see, the loss minimizes over time, meaning our model gets better with each epoch. We can also plot this progress as we have saved the learning history under the history variable. For this we can use matplotlib, which we imported as plt. So we start by providing a label for the x-axis, which will be the epoch number. The y-axis will be the loss magnitude. Now we add the actual graph to the plot by saying plt.plot, and from our history variable, we call the history dictionary, which has got a key called loss. The fact that we can call .history on our variable history is something that the developers of Keras implemented. So if you think you have to be super good at programming to know that, just remember that everyone else is also just Googling it to find out. So to finally show our graph, we call plt once again and say .show. As you can see, the loss dropped very fast at the beginning, and then the model improved only a little bit in the later epochs. In general, this is a good trend as we want the loss to be minimized. Let's make a prediction with this model and call model.predict, followed by a single square bracket this time. And let's take 75 degrees Celsius as an input. And the model makes a prediction of 166.9 something. To check whether this is correct, we will do this calculation manually as well. So 75 times 1.8 plus 32. And as you can see, the prediction is not perfect. It is close, but not as good as under the linear regression that we used with sklearn. How could that be if the neuron itself uses the same formula as a linear regression? The answer lies in the way that neural networks learn. The input data used is neither normalized nor standardized and has no fixed range. This means that the loss, so the mean squared error between the prediction and the true value, can be very large. A high loss again means a large gradient, making it super difficult to train the model. You can also see this if you play around with a learning rate. If you change it to 0.02 and just take 10 epochs, the loss and thus gradients will explode and the model will not be trainable. By the way, the other extreme are vanishing gradients, meaning they would be too small to train a model. To prevent such exploding or vanishing gradients, we will normalize our data in the future. But sometimes a simple linear regression model is just the better option, and there is no need to use fancy neural networks. So let's try to implement possible solutions for those issues on a more complex example. We will now try to predict missing weather data. The scenario: the humidity sensor of a weather station has failed. Now a model needs to be set up that is based on historical data in order to approximate current data gaps. And for that, we will need quite a lot of imports. This time I will just copy them. The first imports are the same as in the previous part, so actually they are redundant and not needed if you are still working on the same notebook. But I just added them here in case you skipped the first part. We also have some new modules. You already know pandas from the Python introduction, so this is not new to you. In case you missed the video, pandas is used to work with tabular data, which will be a CSV file in our use case. Then we have datetime, which we will use on the tabular data to get dates into the right format. The train test split from sklearn is something new as well. We will use it to separate our data into training data, which the model will be trained on, and test data, which the model will not see during training. By withholding the test data during training, we can use it later to test the model's performance on unseen data. Let's start to import our weather data, which is stored as a CSV file. The variable name df is often chosen as it stands for data frame, which is exactly what we'll load now. So df is equal to pd.readCSV. Then we have to provide the path to our CSV file, which lies relative to this script in the subfolder data and is called rup_weather.csv. Furthermore, we need to tell pandas that the separator used in this case is a comma. To see the first measurements in the dataset, we call df.head. Neural networks can generally only deal with numbers. Hence, the first column, called Datum, which is German for date, would cause issues in a neural network. To deal with this issue, we want to convert the dates into day of years. We could also just delete this column, but who knows, maybe the day of year might provide a valuable information for a neural network to get insight into something that I might not be aware of. So let's convert it to keep this information. Before we can convert it into a day of year, we first need to convert it into a date format that Python can interpret. Therefore, we take our data frame df and want to overwrite the column datum. Then we say pd.toDatetime and provide the datum column once again, since the information about the date are currently still saved there. Then we need to provide information about the current data format, which we do with the format equals %d for day /%m for month and %y for the year. And taking a look at the data frame, this is exactly the data format used in the current dataset. Next, we want to convert the dates into day of years. We'll put this into a new column, which we will call DOY. And the information stored there should come from the column datum, but as dt.dayofyear, which is just the conversion that is meant to take place. So let us now check the data types of the dataset with df.dtypes. We can see that the column datum now has the data type datetime, and our newly calculated DOY is a regular integer. Next, we need to clean up our data. As neural networks do not like data gaps, we have to remove them from our dataset. Therefore, we say df.dropNA and make it an in-place operation. So now all observations containing invalid NaN measurements are removed within the df data frame. Then we also have to remove the date column, as it has a data type that a neural network does not understand. So we say df.drop and provide the column name, as well as the axis along which it can be found, and again make it an in-place operation. By plotting the data frame once again, we see that the date column has been removed, and we can go on sorting our data into X and Y data. Our X, aka input data, should contain all columns except the relative humidity column, which is supposed to be our target data. Keeping it as an input would not make any sense, as this is the value the model is supposed to approximate. So we drop that specific column with df.drop, followed by the column's name. Our Y, aka target data, should only be the relative humidity. Now we have one data frame for the X data and one data series for the Y data. But as we discussed earlier, we want to withhold some data, which we can use later for testing. For random separation into a training and a testing dataset, we will use the train test split function provided by sklearn. The way we call that function might seem a bit odd, therefore we quickly look into the documentation and see that the function returns a list containing 4 positions. To separate those 4 positions, the easiest way is to provide 4 variables. And the order of those variables can be seen in this example. This order of xtrain, xtest, ytrain, and ytest is fixed and should be considered when we use this function. So I will just copy this part to make sure I do not mix up anything. The train test split should now use our x and y data as an input. Furthermore, we want to set the test size to, let's say, 0.2. This means we want 20% of the data to be put into the testing dataset and take the rest for training. Next, we can provide a random state. You do not really need it, but if you use the same number as I do, you will also get the same random dataset. The last argument will be the shuffle, which will be set to true. As our measurements in the dataset are currently sorted by their date, it is necessary to bring a random shuffle into the dataset. Let us add two print statements to check the shape of the xtrain and ytrain variables and execute that cell. You see that xtrain holds 340 data points with 10 features each. So temperature, wind speed, precipitation, etc. Those will be the training data points for our model. Ytrain holds 340 single measurements. Those are the corresponding target values for the training phase. Xtest are then the input measurements for testing later, and ytest the corresponding target values. If you want to see their shape as well, you can add two more print statements. To make this script a little bit less hard-coded, we will grab the size of the input data and put it into a variable called input size. This should hold the number of features per measurement, which we can find in the shape of our xtrain data. So we just say xtrain.shape and call the second value in its tuple, which is at index 1. You can print this to make sure we select the correct value. We now have x and y for both training and testing. What we should do next is normalizing the data to avoid issues with the gradients as we saw earlier. As our target data y is just the relative humidity, there's an easy way to normalize it. Usually we do not have a relative humidity above 100%, so we can just divide our y data by 100 to scale it between 0 and 1. To make sure that the scaling worked, I will print out the maximum values. As we see, the maximums are below 1, indicating that the scaling of the y data worked. As our x data has 10 features and figuring out an individual normalization technique for each measurement might take a while, we will keep it simple and define a normalization layer, which will be the first layer in our neural network. But before we can use it, we need to fit it to our training data. I will just call it layer and go to keras.layers.experimental.preprocessing.normalization. Next, this layer gets adapted to the xtrain data. Now we are ready to build the actual model. I will again call it model and set up a sequential model. Now we add the normalization layer as the first layer to our model. Then we add the first dense layer. I will choose 128 neurons for the first layer. And this time I will also choose an activation function. I will use a ReLU for this. As this is our first dense layer, we also have to provide the shape of the input data. We will use the input size variable for this, as this already knows the number of features per data point. Next, we can add some more layers. Let's use another dense layer, this time with 256 neurons, and a sigmoid activation function. We then also need an output layer that provides the final output and thus the model's prediction. As we only want to predict a single feature, the dense layer has only one neuron. Now it's time to think about the final activation function. This is crucial in a lot of use cases, and if we do not choose the right one, our model will fail. Remember that we scaled our y data between 0 and 1, and the sigmoid can do exactly that. However, this also means that our model will never be able to do a prediction that is above 1. For this use case, this is okay, as it is not so likely to get a relative humidity above 100%. Just keep in mind that this is a constraint that we put into our model. Now that we have the architecture of the model, we need to set up the optimizer, which will be again stochastic gradient descent. This time with a learning rate of 0.1. Next, we compile the model with model.compile. Specify the optimizer, which we just set up, and define the loss, which will be the mean squared error again. The last step is the training process itself. As we want to track the learning history again, we write history equals model.fit and provide xtrain and ytrain. Specify the number of epochs, let's say 200. And this time we also set a batch size of, let's say, 68. So 68 observations will be passed through the model before the parameters are adjusted. The next batch of 68 observation follows. I execute that cell and wait a couple of seconds until it's finished. To plot the learning history, I will just copy the code from our previous example. You can see that the loss still gradually decreases, so it could be that more epochs might improve the model. As a last step, I want to make some predictions with the help of the test data that we have held back. To make it a little bit interactive, I first want to have a variable that can hold an integer. Then I want to use this variable to pick an observation from our X-test dataset with the help of ilog. Then get the values from this observation and reshape them to the shape the model wants to receive. Then I want to print the prediction that the model makes based on this observation. The selection in those square brackets is just to extract the prediction from its nested list. As we also need the true value, I will also print the corresponding y-test value. You see, we have a slight difference between the prediction and the true value, but this seems to be quite good already. Now you can also play around and change the integer to receive different test values. I think it's quite impressive that we can do approximations that are not too far off the real value with just a couple of lines of code. And congratulations for programming your first neural network. You see, it's not that difficult.